All right, so let's talk about some large learning models and techniques. The first thing I want to do is talk about RAGs, retrieval augmented generation systems. We're going to make our own version of a system like Microsoft Copilot. Now, the first one is incredibly simple, a simple Python script. If I cat rag1, all right, what this does is it just has only 10 possible answers, which are things like go for a hike and admire the scenery and take a yoga class and things like that. And it's going to there's no machine learning in this one. This one's just going to use Jacquard similarity, which is a fancy word for a keyword match. You can ask it a question, and it's just going to take the words from your question and count how many words apply to these answers, and then give you that answer. So this is Python 3, RAG 1, retrieval augmented generation 1. If I say I like to hike, it tells you go for a hike because it found this word hike and it found that it matched that word hike. And so it's done. It's done its job. And this is like an old fashioned search engine, like the way Google used to be. And it's really stupid. So if I write, I don't like to hike, it tells me to hike because it just matched the words. It didn't read the sentence and understand this word don't. So that's not very good. So the next step up is to use an AI, which will pay attention to all the words. So I have the same 10 possible answers and I have the same Jacquard similarity, but instead of just giving you the answer that matches by Jacquard similarity, I I'm going to use that to find relevant documents. That's going to be my retrieval augmented generation. I'll use the keyword to bring in whatever of those 10 questions seem relevant. And then I'll have a prompt I wrote here, which I feed to an AI. And I'm running Llama 2 in the background so it can connect to it by an API. And that's what you see down here. It's running on localhost on port 11434. It's going to call Llama 2 and it's going to send to the Llama 2 the user's question and the relevant documents that it fetched from that list of 10 possible activities. And then it's going to compose an answer. And it's going to show us its work here so it's easy to understand. So if I do Python 3, reg 2, oh, okay, what at least I say I like to hike. And now it will show you, here's what it sent. You are a bot that makes recommendations. You answer in short sentences. This is the recommended activity. The user input is this. Now compile a recommendation. And so the answer is, it wrote some new text telling me to go for a hike. And the difference now is if I say, I don't like to hike, the Jacquard part doesn't understand that, so it gives me the same recommended activity, but the large language model part was able to read this and tell I don't like hiking, so it made up something else. So that's showing more intelligence. And now to see this actually do some good, you made a third one where you actually download a real document from the National Institute of Standards that's full of AI risks. And then you can take that document and it will have something like 80 sentences of possible AI risks. And you can now use the same logic to ask questions and it will look up things in the risks there. So anyway, that shows you how retrieval augmented generation works in a very simple case. You can understand it. And then we can do a little bit more to understand how large language models work. BERT is a bidirectional transformer, and it takes words that come in, turns them into tokens, and then embeds them and vectors. And you can see how these vectors work. So here it's going to tokenize some sentences. Napoleon revolutionized military organization. Napoleon has legacy. Legacy still lives. It encodes them. It puts a 101 at the start of the sentence. It uses a mark for the period between sentences, and it puts a 102 at the end of them. Then it masks 15% of the words randomly. So these words have been replaced by 103s instead of the other token number. So it's going to try to guess those and fill them in. It's going to try to predict the matched word. So you see there's 20% of can and 30% of can, 18% of will, 5% of to. This one we looked at earlier in the description. So you can see how this is how it learns the meaning of words. It learns how likely this word is to appear given the context. And it doesn't actually understand any meaning, but that's how it takes words that are similar and moves them closer together in that high dimensional space. That's how it recognizes similarities of meaning, because these words are likely to be filling in the same gap, and relative meaning between words. It's able to get two, and it gets part of that from this. You have sentences. You take a sentence and you then have a second sentence in your training data that contains paragraphs. And then half the time you replace the second sentence with a random other sentence. And you train your model to tell if the sentences are matching or not. And so you've now trained it how to fill in words that will fit with the words around them in an expected way. And now it's going to know how to put sentences that fit with the sentences around them in an expected way. And that's it. That's the intelligence it has that makes it pass the Turing test. Now, when you read through the text, it will read as if a human wrote it within the structure of the sentences and when sentences are compared to sentences around them. Both of them will make sense in context. That's it, though. It has no idea what it's saying or whether it's true or false. So these get embedded down here. And so you can test this on, for example, sentiment analysis. This is a common task. If you have a corporation, they monitor like Twitter and stuff like that to see what people are saying about your company. And they want to determine if people are angry about your product, if your product is popular, things like that. So rather than making humans read all that, they make AI read all these comments and then make some kind of summary judgment. So you can get movie review data that gives you movie reviews and it gives you the number of stars the movie got. So you can get it take 100 movie reviews and then determine whether you want to call it positive or negative, and then decide how well it works. So I'm able to evaluate the accuracy by saying it's wrong. If it's a 3 stars, then I don't consider it wrong, whatever the answer is, because that's in the middle. But if it's a 1 or 2 star and you call it positive, that's an error. If it's a 4 or 5 star and you call it negative, that's an error. So you can run it through here and see how accurately it is, and you'll see it got 6 wrong out of 100 movies. So it's pretty good at reading paragraphs of text and then deciding, was that generally positive or generally negative? All right. And the last one worth mentioning is the embedding. What I mentioned before, you can see the BERT is pre-trained with an alphabet of something like 20 or 30,000 English words, and you can see some of them. It just has all the common English words in it. So now you can tokenize a sentence. It will just have numbers assigned to each word, and then you can embed them into vectors. And here you see what I showed you earlier. When it's done, it will now give you 768 dimensional vectors for each word. And as you can see, the two banks that mean the same thing have very similar vectors, and a bank used in a different context that has a different meaning gets a very different vector. And so you can calculate the similarity of vectors in this high dimensional space by taking the cosine between the angles. And so you can see for different meanings of bank, it was 69% similar, but for the two similar meanings of bank, it was 94% similar. So you can tell words that are synonyms and words that are not synonyms. And so you can play with this. You can get the vector that move similarity between boys and men, boy and man, and you can get the similarity between man, the vector that goes from man to boy, and the vector that goes from woman to girl. And you'll see that these are very close, similar vectors. And so on. You can find synonyms and so on. So you can practice it. It can do all these things. It can find synonyms. It can determine the sentiment. It can take the difference in meaning and compare it to another difference in meaning. And it does all that without understanding any of the words or sentences based on just sort of a statistical analysis of all the data that came in. So, like I say, this is why it fools you into thinking it can read when it can't. All right. So that's what I wanted to show you about how LLMs work. Let me stop this one.